screen visible?
Yes, ma'am.
So before starting with today's class, so first of all, I want to ask you, like, do you have any doubts regarding what this Nyquist stability criteria is, or how we are getting, how we are plotting the Nyquist plots and all? We will do yesterday in yesterday's class also we did 1 or 2 examples. In today's class also we will do a few more examples in order to make things a little bit more clear, because because Nyquist criteria, the basic the mathematical preliminaries we have already talked about. So now we are looking into what how that is being used in order to find out, or in order to assess the stability of a closed loop control system. Okay, so in all the cases, whenever we are studying the closed loop stability, in most of the cases we have seen that we are generally concluding or inferring something about the stability of the closed loop system by studying the open loop from the open loop transfer function, right? So in this, for this Nyquist stability criteria also, what we are doing is that we are plotting for a given open loop transfer function. So for that open loop transfer function, we are plotting or rather we are drawing something which is known as a Nyquist plot. And from that Nyquist plot, we are seeing that how many encirclements of the critical point, that is the point -1 plus j0, how many encirclements of this point is being done in the anti-clockwise direction. So depending on that, we are going to infer about like whether the closed loop system is going to be stable or not. Let's try to do one more example, a few more examples in today's class. So first of all, so this is an open loop transfer function which is given to you. Okay, so in general, we are considering that the value of hs is equals to 1, or this is, so if I write GSHS is equals to this thing, so we are generally considering, so if this is equal to the forward path transfer function, so that means that the value of hs is going to be equal to 1. Okay, so this is, let's say, the given transfer function for the open loop transfer function which is given. So what we need to do is that we have to draw the corresponding Nyquist plot for this transfer function, right? And for Nyquist plot, what we need to do is that first of all we have to draw the Nyquist contour, and from that Nyquist contour we have to map that Nyquist contour onto a plane, and that mapping, the result of that mapping is the Nyquist plot. Okay, so in this case you see that we have one pole on the right half of the S plane. So we have one pole on right half S plane. We have one pole at right half S plane and another pole at origin. Right? So in this case, so what will happen? So that means the value of P is equals to 1. Right, so P being the number of number of poles that are present on the right half of the S plane for the open loop transfer function. So P is equals to 1. So the Nyquist, and since we have a pole at the origin, so that means we will have to indent the Nyquist contour around this origin or this pole in the anti-clockwise direction. So the overall, this will be your Nyquist contour. Okay, so what we will do is that we will take each and every section of this Nyquist contour and we will map it onto the GSHS plane. Okay, so first of all, for that what we will do is that we will just rewrite these expressions. So GSHS can be rewritten as A of k multiplied by 1 plus S by A divided by S into S minus 1, right? And also you can simply substitute the value of S with j omega. So in that case you will get, let's say, k dashed is equals to A into k. So that means it will be k dashed into 1 plus j omega by A divided by j omega multiplied by j omega minus 1, right? So from here what we can do is that we can rationalize this transfer function and we can write it out in terms of real part plus imaginary part. So if you write the real part and imaginary part, so it will look like this will be, so I'm writing the final expression. You have to do the derivation, you have to do the rationalization on your own. So k dashed 1 plus 1 by A divided by 1 plus omega square whole square plus j of k dash into 1 minus omega square by a divided by omega into 1 plus omega square. So there is no whole square. Okay, so this is for the real part and the imaginary part. So first of all, what we'll have to do is that, first of all, we'll consider this part. Okay, so this is, let's say, C1 dashed. So for C1 dashed, so we have to vary the value of omega from 0 plus to plus infinity. Okay, so for omega equals to 0, or before going to that, let me write what is the phase angle for this g of j omega, h of j omega. Right, so the phase angle can be found out from here. So from the numerator term, you have tan inverse of omega by a, then you have minus 90 degree for this j omega, and you have minus tan inverse of minus omega. And tan inverse of minus omega is nothing but pi minus tan inverse of omega. So you can rewrite this expression and it will come as tan inverse of omega by a plus tan inverse of omega plus 90 degree. Okay, so now we will find out that what will be the at omega equals to 0, at omega equals to infinity, where are how the plots look like. Okay, so for omega equals to 0, we will have that the real part is equals to minus k into 1 plus a, and the imaginary part is equals to infinity. And if you write the phase angle, so the phase angle would be equals to plus 90 degree, right? And for omega equals to plus infinity, so the real part is equals to 0, the imaginary part is also equals to 0, and the phase angle is minus 90 degree, right? And so this is the starting point. So for that, so for this part C1 dashed, we have omega, at omega equals to 0, we have this point. These points are done. Okay, so then we will see that we will try to find out what is the, if we take that the imaginary part of the gh of j omega is equals to 0, so that means that the intersection with the, this means that intersection with the real axis, right? So if we equate this imaginary part is equals to 0, so this was the imaginary part. So if we equate it, we will find 1 minus omega square by a is equals to 0. So 1 minus omega square by a is will be equals to 0, or you can write omega will be equals to plus minus square root of a. But a is obviously given that a is greater than 0. And at this point, so if you find out the magnitude of the given transfer function at omega square is equals to a, so that magnitude will be equals to minus k, right? So this is for C1 dashed. So let's try to plot it for C1 dashed. So for C1 dashed, we saw that at omega equals to 0, the real part is minus k into 1 plus a, imaginary part is infinity, and the phase angle is plus 90 degree. So this will start, so this part, this is k minus a, k into a plus 1. So it will start, and the value of at this point, this is j infinity, right? So this is that point. So from here it will start and it will move, since the phase angle is plus 90 degree, so that means it will start moving, or it will start moving parallel to this 90 degree axis. So like almost parallel to the 90 degree axis. So you can say that it is sort of moving like this. The exact shape, in order to find out the exact shape, obviously you have to find out different, find out the values of, for different other values of omega, so that you can get the exact shape. So this is like, you can say this is a rough shape of the Nyquist plot. Since we know that for the Nyquist plot, basically we are not exactly, we don't exactly want the very accurate shape of the Nyquist plot. Okay, so this is coming from this point and it is going to here, and at omega equals to plus minus square root of a, it is intersecting the real axis. That means that the imaginary part is equals to 0, and at this point the value of gain is equal, the value of real part is equals to minus k, right? So from here what is happening is that, so this value of omega is increasing, it has reached from 0, it has reached to root over a, and then it will move to omega equals to plus infinity. For omega equals to plus infinity, you see that the real part is equals to 0, imaginary part is equals to 0, means that the plot will end at the origin and the phase angle being minus 90 degree. So that means that the the angle which it would follow, or it will be sort of parallel to the minus 90 degree axis. So this is my minus 90 degree axis. So it will start from here, move till here, and then follow up curve and then end at this point. So this is the part corresponding. So this will be, you can say this is the part which corresponds to the C1 dashed portion. Okay. Similarly for C2 dashed, what is for C1 double dashed, what we do is that we take simply the symmetrical of C1 dashed about the real axis. So you can say that it will be just the mirror image of this one. So it will come like this. It will, so for this part, this is the symmetrical part, and for this will be symmetrical to here. Okay. So this is for C1 dashed and C1 double dashed. Then we have C2 and this is C3. So for C2, what we do is that for C2 means that we have to find out the limit for r tends to infinity gs of hs at s equals to r e to the power j5. Okay, so if you substitute the value of s in this one, you will get that this is nothing but e to the power 0 e to the power minus j5, right? So in this case, the value of phi is changing from plus 90 degree to 0 to minus 90 degree. But the corresponding mapping, so it maps at the origin, and the phase angle it changed. So this minus phi is varying from minus 90 degree to 0 degree to plus 90 degree, right? So that means that there is a angle change, or the direction of it changes from minus 90 degree to 0 degree to plus 90 degree. That this is from minus 90 degree, it goes to 0 degree, and it has changed its position and it goes to the minus 90 degree side. So to the plus 90 degree side. So in this case, you can simply write, you can also draw this one in a different way. So let's say it started from here, it came here. So this was for C1 part. Okay, so here it is actually there is a sign change, so you can draw it like this also, provided that this part, this is basically something which is almost 0. So effectively, just to draw like how the angle is changing, so that means it is coming from here going till here. So from here corresponding to C2, there is an angle change from minus 90 degree to plus 90 degree. Then you have for C1 double dash, this is coming here, then it is moving towards this side. Okay, so for C2 it is done. Then we'll find it for C3. For C3, what we'll do is that we'll find the limit s tends to 0. Sorry, epsilon tends to 0. Similarly, gs of hs at s equals to epsilon e to the power j theta, and it will come out as minus infinity e to the power minus j theta. So that means it will be an infinite arc with a negative in the negative side, and the phase angle, that is phi, that is minus theta, that will change from minus 90 degree to 0 degree to plus 90 degree. And in this case, theta, it changes from plus 90 degree to 0 degree to minus 90 degree. Sorry, this is from minus 90 to 0 to plus 90. So from here it will be just the opposite. From minus 90 it will go to 0 to plus 90 to minus 90. Sorry. So from here what it will do is that it will follow an infinite arc and it will end over here, right? So it is moving from minus 90 degree to plus 90 degree. So this will consist of the whole Nyquist plot. Okay, so in this Nyquist plot, you see that this point, this is the critical point, minus 1 plus j0. So minus 1 plus j0 is actually dependent, or you can say that if you adjust the value of this gain, if the value of this k is greater than minus 1, in that case the encirclement of this point is done once in the counterclockwise direction, right? So in that case you can write that the value of n is equals to 1 and n, this is equals to p. So that means the value of z is equals to 0. So that means we have no closed loop poles on the right half of the S plane. So it indicates that for k greater than 1, the system is stable. But if the value of k is less than 1, so in that case, so if it is less than 1, so that means this value of k will lie somewhere over here. So in that case, it will have, so for k less than 1, this point is lying beyond, it will lie somewhere over here, let's say, like this minus 1 plus j0 will lie somewhere over here. And here you see that it is encircled, that the value of n is equals to minus 1, because this is encircled once in the clockwise direction. So n will be equals to 1. So the value of z will be equals to p minus n, which will be equals to 2. So that means that you have two closed loop poles on the right half of the S-plane. For this value of gain, k less than 1, the closed loop system is going to be unstable, and for k greater than 1, the closed loop system will be a stable one. Okay. A similar way, you can find out, or you can draw for other examples also. So this is, let's say you have a transfer function which is given by this. Okay, so the first step obviously would be you have to find out g of j omega, h of j omega in terms of real plus j into imaginary part. Also you find out what is the phase angle of this. Okay, so you have to find out this. Then you have to draw the corresponding Nyquist contour. In this Nyquist contour, you see that there is no pole, or no pole on the imaginary axis, right? No pole on the imaginary axis means the Nyquist contour will look something like this. So this part is C1 dashed, this is C2, and then this is C1 double dash. So we have to map for corresponding to C1 dash, C2 dash. C1 dash and C2 dash will obviously be mirror image of each other, and C2. We have to map it into the GSHS plane. Okay. So in this case also, if you just simply substitute or do the calculation, you will get that the real part is equals to 4 of k into 4 omega square minus 2 divided by 1 minus omega square whole square plus 4 omega square, and the imaginary part is equals to k into 5 omega minus omega cube divided by 1 minus omega square whole square plus 4 omega square, right? And the phase angle, so this phase angle is equals to tan inverse of minus omega by 2 minus 2 tan inverse of omega. So this you can write, so this will be pi minus tan inverse of omega by 2 minus 2 tan inverse of omega, right? So then you will have to find out for C1 dashed, so for omega equals to 0 where the point will lie, for omega equals to infinity where the point will lie, and you have to see that if you equate what are the points at which this polar plot might be crossing the real axis and the imaginary axis. So you equate this part to be equals to 0, and you will get this point. So if you equate this real part is equals to 0, you will get this point. You can find the value of this point from the magnitude. And if you equate the imaginary part, this imaginary part is equals to 0, you will end up with this point. So it will be this point, right? So from this plot, you can say that, so it will start somewhere over here. So for 0 plus, the value is 2k. So it will start over here, and then it will move. It will cross the imaginary axis at this point. It will go to the right half, and then it will cross the real axis at this point. Then it will turn around and come back to here, which is nothing but this is the omega equals to infinity point, right? So it goes something like this. And for the C1 dashed part, so C1 dashed will be nothing but just the symmetrical or the mirror image of the first part. Okay, so the mirror image will be, so this is here and this is here. And you have C2 dashed. For C2 dashed, what we will have for C2, what we have is that, so you will simply put limit r tends to infinity GSHS, right? For s equals to r e to the power j5, and from here you will get, it will be 0 angle minus 5. So this minus 5 will range from minus 90 degree to 0 to plus 90 degree, right? It is coming from minus 90 degree to 0 to plus 90. That's why there is a change in the direction. Otherwise, just if you just take the symmetrical, so that means it would have been that you won't know how the direction of C1 double dash will look like. But since at this origin, that is at corresponding to this C2 part of the contour, you are getting a change in the direction, and that change is happening in this way, that is minus 90 degree to 0 to plus 90 degree. So that means after here it is changing, it is going to minus 90 degree, then it is crossing 0, and then it is moving to plus 90 degree. That's why it is going in this direction, and then finally it is completing the Nyquist plot. So in this case also you see that this is the value of 2k, and this is the point which are the encircling point, right? So now if the value of 2k that is greater than 1, so that means in that case the number of encirclements of this point n is equals to minus 1, right? So for 2k greater than 1, so that means you can write k greater than half. So for that case, the value of n is equals to minus 1, because this point is being encircled once in the clockwise direction. So that means minus 1 times in the anti-clockwise direction. And the value of p is given is equals to 0. So that means the value of z will be equals to plus 1, and it implies that the system is an unstable one. But if the value of k is less than half, in that case what is happening? If it is less than half, so that means it will move towards this side, and this minus 1 plus j0 that will not be enclosed. So this point will lie somewhere over here, right? So that means this point, this minus 1 plus j0, it's not enclosed by the Nyquist plot. So that means n will be equals to 0, p is also equals to 0, so that means z will be 0, and we can say that for this gain the system will be, the closed loop system will be a stable. Okay. So is it clear how to draw this Nyquist plot? Okay, so then I'll give you a few more examples to practice at home. So this is one of that. I'll give you more examples or practice problems at the end of today's. So next, let's see, let us say that you have, let's do a different kind of an example. So let's say that for this is a Nyquist plot which is given to you. Okay, so you have an open loop transfer function, and for a particular gain of the open loop transfer function, this is how the Nyquist plot looks like. Okay, and it is given that the open loop system does not have any poles on the right half of the S-plane. So that means the value of P is equals to 0, right? So now you have to find out whether the closed loop system is going to be stable for unity feedback. So this is my minus 1 plus j0 point. So in order to find out the stability, we have to find out how many encirclements of this minus 1 plus j0 point is happening in the Nyquist plot. So here you see you have one clockwise encirclement, and the other one is this clockwise encirclement. So we have two clockwise encirclements of this point minus 1 plus j0. So that means the value of n will be equals to minus 2. Right, from there if you find out the value of z, so z will be equals to 2, right? So from here you can say that the closed loop system is going to be an unstable one with two poles on the right half of the S-plane. Now let's say that you have adjusted the system gain. So you have adjusted the system gain in such a way that now this minus 1 plus j0, it is lying at this point P. Okay, so it has shifted from here to here. So now let's see that whether the system has become stable or not. So if minus 1 plus j0 is lying over here, so the total number of encirclements will be 1 in the anti-clockwise direction and 1 in the clockwise direction. So that means it will be, so n will be equals to minus 1 plus 1, which will be equals to 0, right? So in that case, the value of z is also equals to 0, and the closed loop system is going to be a stable system under this condition for that corresponding value of k. Now, if you change the value of k again, such that this minus 1 plus j0 is lying somewhere between in this third loop. Okay, in this case also, if you calculate the number of encirclements, so this is 1 in the clockwise direction and 2 in clockwise direction. So you have 2 clockwise encirclement of minus 1 plus j0. So that means again the value of n will be equals to minus 2, and the closed loop system will again become unstable. So from here you can say that basically by changing the value of gain, of the gain of the open loop transfer function, we can control whether the closed loop system is going to be a stable system or an unstable system. So this is, you can say, this is a conditional stability for the system. So that means only for a particular range of the gain, for that particular range only the system is going to be stable, and for all other gains the system will go into, the closed loop system will go into instability. So this is known as conditional stability. So just by analyzing the number of encirclements of this point -1 plus J0 in the Nyquist plot, you can comment on whether your system is going to be, the closed loop system is going to be a stable one or an unstable one. So these are some of the practice problems which you should do at home. In case if you face any difficulty, you can ask me. So till now we have seen that we can comment on the absolute stability of the closed loop system from the Nyquist plot. Okay, so we can either say whether the closed loop system is going to be a stable one or an unstable one. But sometimes obviously that information is not always sufficient, right? So we need to know that how much stable the system is, or rather how much gain we can change so that my system still remains in the stable region and doesn't go into the unstable region. Okay, so that is the measure of relative stability. Okay, so now let us say that we consider two systems. So both of these two systems are stable in the closed loop. Okay, and the pole positions are given by, for system A it is given at this position, and for system B it is much more closer to the to the imaginary axis. So you can say that the degree of stability for system A, that is obviously better than the degree of stability of system B, because these poles are lying closer to the imaginary axis, and the more you go closer to the imaginary axis means that you are prone to having oscillations in your system, and you are at the verge of going into instability. Right. So for these kind of systems, if you try to plot the plot the polar plot, so a polar plot or the Nyquist plot. So let's say that for this system A, the polar plot looks something like this, right? And for plot B, the polar plot looks something like this. So by comparing these two figures, you can see that the distance of this polar plot from this -1 plus J0, so this distance is much more in the system A compared to that in the system B, right? So